You don't need to learn more design patterns. You're already using the same 7 over and over again. You just call them different things: pub, sub, event-driven, observer, different names, same decision. You've already seen this. A retry loop that made things worse. An event that triggered something you didn't expect. Retry, circuit breaker, queue, different implementations, same behavior. The problem is not that you don't know enough patterns. The problem is you don't see what they're actually doing to your system. Because patterns don't explain behavior, they hide it. So instead of learning more patterns, we compress them. Because when systems are under pressure, you don't see 23 patterns. You see the same forces repeating. 7, not 23. 7. Boundaries, coordination, state, control, creation, failure, evolution. Let's make this real. Imagine a simple system. A user places an order. You have an API, a payment service, a database, maybe a queue, maybe an event. Nothing complex. Now watch what happens when this system is under pressure. First, boundaries. You think you have separate services, API, payment, order, but the moment a payment fails and your API needs to know and your order state needs to change, that boundary disappears. Because the system needed to coordinate and your boundary couldn't stop it. Because failure crossed it. So the real boundary is not where you drew it, it's where the system stops propagation. Then coordination. The API calls payment, or emits an event, or puts a message on a queue. Doesn't matter. The moment payment fails, the rest of the system is affected. You didn't remove the dependency. You changed how it propagates. Then state. Did the order succeed? The API says yes, the payment says no, the database says maybe. Now you have multiple truths, and your system has to decide which one matters. And your system has to act anyway. That's not a database problem. That's a state decision. Then control. Payment times out. What do? Retry? Now you increase load. Queue it? Now you delay the problem. Fail fast? Now the user sees an error. Every choice changes how the system fails. That's control. Then creation. Who decided? That payment is called synchronously or asynchronously or through a queue. That decision defines coupling, flexibility, failure behavior. Creation is control over composition. Then failure. Where does this system break? At the API, at payment, in the queue? If retries keep firing, you don't get one failure, you get many. That's not bad luck. That's structure. You didn't get unlucky. You got exactly what you designed. Then evolution. Now you need to change payment provider. Can you? Or is it tightly embedded in your API, your state model, your retry logic? If it is, change becomes dangerous. That's evolution. Nothing in that system was advanced. No exotic patterns, and yet every single one of the 7 showed up. Not because you chose them, because the system forced them. This is not unique to software. In physical systems, pressure finds weak points. Energy follows paths. Failure doesn't stay contained. Software does the same. You're not designing patterns. You're shaping how the system behaves when reality hits it. Pub, sub, coordination, retry, control, CQRS, state, strangler, evolution, different names, same decisions. So what are the 7 again? Boundaries, where things stop. Coordination, how things influence each other. State, where decisions become real. Control, how the system behaves under pressure. Creation, who controls composition. Failure, where the system breaks. Evolution, how the system changes over time. So stop asking, which pattern should I use? Ask, what is this system doing when it coordinates, when it stores state, when it is under pressure, when it fails, and when it changes? That's architecture. You don't need more design patterns. You need to understand the few decisions that all of them are trying to describe. If you want to go deeper, I'm breaking down each of these 7 patterns, one by one, and what they actually do to your system under pressure. Subscribe if you want to see how each of these actually behaves in real systems, not just how they're described.